Okay, so maybe I'll start by introducing the speaker today, Jibin Zhao, who received his PhD degree from Shanghai Jiaotong University in China. He was a research scientist at RIKEN Brain Science Institute, and then joined as a unit leader and became the team leader for the Tensor learning team. He's also a visiting professor at Tokyo University of Agriculture and Technology and Saitama Institute of Technology in Japan. His research interests include machine learning, tensor factorization, tensor networks, and brain signal processing. He's very prolific, published more than 150 scientific papers, and his 2 monographs on tensor networks. And he's quite active in serving the community as well, being an area chair for many top-tier ML conferences, and he has organized several workshops at NeurIPS and Ichikai. Jibin, looking forward to your talk. Please take it away.
Thanks to Volkan for kind introduction. It's my pleasure to have this opportunity to give a talk today. Today, I will talk about, the title of my talk is Efficient Machine Learning with Tensor Networks. And as we know, that successful deep learning actually highly rely on the 3 factors. There, we have a huge number of big data sets and the high performance computation, and also big models with a huge number of parameters and the complex models. And the tensor network actually is a basic mathematical tool. It was widely studied in quantum physics, and it also be useful to process the large data or high dimensional data processing, and can be developed for the acceleration of computation. And quite recently, it was applied to also develop the new new deep learning models and algorithms. So today I will talk about 2 topics. First one is learning from incomplete and limited data. And second is parameter efficient machine learning models. So in many applications, we have multi-dimensional data. For example, in recommendation system, we have a user item and along the time purchase history. Such data has multi-dimensional structure. And we don't have a lot of samples. So like traditional machine learning problems, we have a huge number of samples, and we can train the deep neural network. And in knowledge graph data, we know some connections or relations between the entities. And our goal is to capture the information from such data and to make prediction for the missing values. For such kind of data, the data is multidimensional structure, and we don't have a lot of huge number of samples. So we need to find a method to capture well the data structure information and to fit a model to be better generalized to the missing values. So such task is learning from an incomplete tensor to predict values for unobserved positions. So then the tensor completion method is very popular to solve this task. And the optimization problem is formulated as shown here. We try to solve this optimization problem. First one is fitting error. We try to find a good estimation to the observed data Y in the observed positions. And depending on your noise assumption, you can choose different norm as such loss function. And the second part is structure regulator, which is a key factor to ensure your model is good generalization to the missing data. And the challenge is how to obtain the best data efficiency. That means we use a smaller number of data points to fit the model and to make generalized to the missing values. The second is efficient optimization. So most tensor completion method can be summarized into 2 different type of approach. First one is we can use a non-convex relaxation to convert the low rank constraints to the nuclear norm minimization. Because the low rankness assumption is already demonstrated to be a good structure regulator to have a good generalization. But such convex optimization is easy to optimize, but the problem is not very scalable. Another type of approach is we assume the data, estimation data, satisfy a particular tensor network structure. Then we try to learn the latent factors in the tensor network structures. But the problem is it's difficult to choose the optimal rank, and also difficult to find the best tensor network structure or a topology. Depending on your applications, you can also use prior knowledge like smoothness, non-activity, or other set information from other data sets. So in hyperspectral satellite image, we usually need to do the denoising task. And because such image have a high resolution and it's a huge image, it's usually not showing the low-rankness on the globally. So people are usually use the non-local technique. The idea is we find the smaller patches and we group many similar patches together to build a tensor. Then such tensor satisfies the low rank assumption. Then we can apply the low rank tensor approximation to do the denoising task. Also, when you're missing data, missing patterns is not uniformly distributed, like such as the whole slice missing or whole fiber missing, the originally low rank assumption or low rank approximation doesn't work well. So to solve such issues, we consider the low rankness is not on the original data space, but on the transformed space. So then we can convert our optimization problem to the nuclear norm minimization under the linear transformation. And given the fitting error smaller than a scalar. Based on such framework, we can also have a theoretical guarantee for the error bound. But how to choose a linear transformation become a new problem to solve. Here we show the one example, one particular linear transformation, which is we use a tensorization as a linear transformation. This procedure can change the low order data to the high order data. After that, we assume that high order tensor can be represented by the tensor network structure, and finally to do the reconstruction. And to solve this problem, we combine the two different types of approach, that fitting error is same, and we assume our estimation satisfy a tensor network structure. In particular, here we show the tensor ring structure, and we learn the latent factors G1 to GD. But to avoid the choose rank manually, we impose a low rank structure to the all core tensors. Instead of we impose a low rankness on estimation Y height, we change the low rankness to the core tensors. Then we can minimize the nuclear norm on core tensors. Since all core tensors has much smaller size than estimation Y, based on this, we can further improve the computation efficiency. So now the question is why the tensorization is useful and how the tensor network can be better represented such data. So now I give a simple example to show the tensorization procedure. Given an image, and the first step, we divide the image as several patches. And we concatenate the patches along the additional mode. So we generate a tensor, 3-order tensor. Then such procedure can be repeated again for each slice matrix to further divide as smaller patch and concatenate them. And finally, each patches can be a vector. So put them back together, we get a high order tensor. So if we use tensor network graph notation to represent such procedure, we can see from these graph notations, the node represents data and the number of edges represents the order of data. So the matrix have 2 edges. So we convert this to a high order tensor by divide the row index as 3 and same to the column index. Then we combine the index together I1 to G1, I2 G2, I3 to G3 to get a new tensor, to build a new tensor. So if you look at the third index 3, which shown as blue, which if we impose low-rankness on mode 3, that means we can capture the correlations or dependency between these 4 patches. And if we consider the first index, we capture the dependency or correlations between the each pixels in the smallest patches. So that means tensorization procedure give us an opportunity to explore the correlations of patches in multi-scales. And the next, what is a tensor network? Actually, it's a natural generalization of tensor factorization, which is for 3D tensor to much more high order tensors. And we can use tensor network to represent the n-order tensors as a contraction of n small tensors. So in physics, this is usually used to describe the quantum many-body system. There are already some popular tensor network structure like tensor train, hierarchical Tucker, and the PEPS Mila. So before introduce later, we first briefly introduce tensor network operations by using such diagram. And if we multiplication of 2 matrices, we can represent it by such graph. We simply connect the common index between A and B. The connection means we do the contraction between A and B. It's a summation along the index G. If there's no connection, it means tensor product, or we call the out product, same thing. And in high order tensor case, multilinear product is very commonly used. For the multilinear product, we must give the index to indicate which mode you need to do the contraction. And beyond the tensor train models, we also introduce a more generalized model, which called the tensor ring decomposition. So the idea is we have n or core tensors, and we do the circularly contractions, which have a loop structure. To understand it, given an element, we have n indices. According to these n indices, we can get out a sequence matrix from each core tensors according to each index. Then we do the sequential product of all the matrix, and later we do the trace operation to get the scalar. To further enhance the model expressiveness, we also introduce the fully connected tensor network. So now we consider the connection between all core tensors. They have the connections. And the big advantage of such models, they have the transpositional invariance. That means if the original data X, we can permute arbitrarily or randomly, but the result is invariant. But the disadvantage is very obvious. We have much more parameters, which has an exponential scaled to the n, the order n. But the theory also shows the relationship between the unfolding matrix rank and the tensor network, a fully connected tensor network rank. So that means in practice, even we have many connections, but each connection have very small rank R. However, in real applications, we don't know how to choose tensor train or tensor ring or which tensor network is best suitable for our data. So some example shows even probably arbitrary tensor network, probably the optimal or the best models for the data set. So the question is how to learn an optimal tensor network structure from the data. And this problem is difficult because even for the 9-order tensors, there are 6 to 8 billion candidates. To solve these issues, we first encoding the tensor network as a graph notations or graph representation. The context is core tensors V, and we encode the connection between core tensors as an adjacency matrix. So the zero means there's no connection between the first core with first core and the first core with the third core, no connection. And then the number means the connection. Number means the connection and the rank of these two cores. So because tensor network usually used to compress data, so we try to find the tensor network structure or topology, which has the high maximize the compression rate. So we try to minimize the compression rate, maximize the compression rate over the A, the adjacency matrix. But the A is discrete value is not easily to solve by continuous optimization. So we develop algorithm by evolutional algorithm to solve such problem. Now let's talk about supervised learning for missing data. And our data features have missing values under the true label Y. Our goal is to learn the classifier F hat, which is the best approximation to the true classifier trained on the complete data. And we also assume there is a function G first to do the completion of the data from X to make reconstruction of data, then train the classifier. But simply do the two-step sequentially, there are some problem because if we do the completion independently, for example, given an image, we don't know how to exactly recover of original data. It's 3 or 8. Because the label information is not used, it's ignored. So that means such procedure cannot ensure the statistical consistency of a classifier. Then we propose a simultaneous optimization to solve this problem. And for completion, we assume the sparse coding for the completion part. Each data point can be represented by the overcomplete dictionary matrix with very sparse coefficients. And our loss function can be shown here. This is the classification loss based on the reconstructed data X height. And the reconstruction data X height can be represented by the sparse coding procedure with overcomplete dictionary and the very sparse coefficients. Then we can learn the theta and the dictionary D and the coefficients alternative by the optimization. And theoretically, we also prove that if some condition satisfied, we can prove the such classifier if the classifier is successfully classified the reconstructed data point, it can be also successfully classify the original data point. So that means we don't need our reconstruction is exactly same with the original data, but we try to keep the classifier hyperplane is same, consistent. So this condition means this epsilon means the distance between the reconstructed data to the boundary. If such distance is larger than the moment between the reconstruction and the original data, then we can guarantee the classifier is same as can be classified the original data very well. Also, it shows by the experiment results that if the epsilon larger than G, we can always successfully classify. Now, we also found if the sparsity is high level sparsity, like sparse coding, we have a high level sparsity, and such condition can be easily satisfied. Some results show that the performance is much better than using the sequential approach by completion independently and the training classifier, and also some other method. And the missing pattern can be random missing or even the irregular missing path. So even half letters are missing, we can reconstruct such image, but we don't require the reconstruction is exactly same as original data, but we want to the reconstruction keep the same classes. So next, I will talk about the tensor network for efficient model. Now, because many many new models like fundamental models like GPT, they have the very huge model parameters. And also the theory shows that over-parameterized deep learning models can have a double descent and can avoid overfitting problem and give the good performance. But to reduce the memory efficiency or to reduce storage and also energy efficiency, we still want to remove the redundancy from the parameters. So the task is how to compress the weight parameters, but keep the comparable performance. And also the strategy should apply, should be compatible to the standard algorithm. We don't want to use a new algorithm to solve this. And furthermore, if possible, we also hope to improve the computation efficiency. So the compression of weight parameters can be done during training or after training. Today, we will talk about compression during training from the scratch. So this is the standard fully connected layer. And we assume the weight parameter W is huge. We try to remove redundancy of W. Now we tensorize W to a high order tensor. Then we represent it as a tensor train format. By using such representation, the number of parameters can be reduced significantly by the this root of original size. But there is a rank R square, which means if the structure have a low rank, we can get much higher compression. But if the rank is high, the compression is performance is low. And next, to ensure the computation of this more conveniently, we also need to tensorize the input layer to a high order tensor. Then we can apply the tensor network operations for efficient computation for this layer. Just simply connect the individual mode. So now we also show how the algorithm like gradient descent and back propagation doesn't affect even we change W as a tensor network format. So we try to optimize the core tensors G instead of optimize the W. So the key point is how to compute the gradient of core tensor G on the tensor network. Because tensor network are all multilinear operations. So the gradient can be computed very conveniently by simply remove this core tensor and make contraction of all rest core tensors. So finally, we can compute the gradient tensor as the gradient of this core tensor. But the input layer is still ordinary data, which is a vector or matrix. So one paper proposed a new idea to change the input layer also as a tensor network structure. So the project, they use a nonlinear mapping for each feature X to a two-dimensional vectors. And this idea actually is inspired by quantum system. The value means the probability of this value to be 0 and the probability of this value to be 1. And this vector is normalized. L2 norm is equal to 1. So this is can be considered as a quantum state. Then after doing this nonlinear mapping for each feature, we can do the tensor product for all the features. We generate a rank 1 tensor. So which is shown as a tensor network format. However, the dimension is increased dramatically from the d-dimensional data to 2 power d. But they show that you even use such input layer and the weight compression as shown in previous slides, they can achieve very good performance on MNIST by using single layer, just one layer. And this method also quite related to the kernel method. But in kernel method, we use the kernel trick to avoid nonlinear mapping explicitly. But here they use nonlinear mapping explicitly by just compress the weight to make it suitable or to tractable. Such idea, compression idea, can also apply to the convolutional neural network to compress the kernels. But some researchers show that if we have a well-trained models, the kernel doesn't show the low-rankness. However, if we reparameterize the weight as the tensor decomposition structure, then we learn from this initial point from the sketch, we can even reduce the generalization error. And the theory shows that higher compression can give us smaller generalization error bound. So in multimodal learning, we have several different modality data, and usually we need different neural network to get a representation of different modality. After that, multimodal fusion of all features and then create another additional layers to give the output. So the key point is here is multimodal fusion. It's same to apply to the visual question answering, and the multimodal fusion is the key point. So the standard way is to use average or concatenation or summation to do the fusion. But here we show that tensor product of tensor network format can be a very useful operation for tensor fusion. Such fusion contains a very rich information, which include the linear features and the bilinear interaction between pairwise modality and the trilinear interaction between all three modalities. And also the result shows that if we use all information, it's much better than we remove any one of the interaction information. But the disadvantage is our dimension increase dramatically because using tensor fusion. And furthermore, if we want to capture more information by using the tensor fusion, the one idea is to concatenate the features from different modality. Then we do the tensor product of F by itself for P times. So we generate a P order tensors, so which contain more additional information, which has intramodal interaction and a high order interactions. We can see from here as an example. But again, the dimensionality is increased dramatically, which is exponentially scaled with P. To solve this problem, we must use the weight compression for the next layer. We assume that our weight for next layer must be represented as a tensor network. So by using this, we can not only to reduce number of parameters from exponential scale to P to linear scales, but also the computation is very fast due to the tensor network operations. That means we don't need to compute tensor fusion explicitly. We just compute the F with a contraction with each core tensor individually. So finally, we have a more expressive power of models with not much increase of number of parameters. When we use multimodal learning for the time series data, and if the time series data is imperfect, like corrupted by the noises or some missing data point at the time point. So the question is how to learn robust representation from imperfect multimodal learning. And we can see that if the data has missing values or the noises, the low rank structure always is broken. So which means the rank will increase by such imperfect data. So based on this phenomenon, we assume we first use tensor fusion for each time point. We get a tensor fusion. Then we do the summation of along all time point M, and we assume M is low rank. If the data is incomplete or there is some missing values, we can use low rankness as regularizers in our loss function, which is a good strategy to improve the robustness for multimodal time series data. Now also in the time series data, the RNN-ISTM is the most popular and successful models. But in last year, one paper mentioned RNN and ISTM actually don't have long memory from a statistic perspective. That means if we compute the autocovariance and we do the summation of autocovariance, if the summation is converged, that means it has short memory, and otherwise it has long memory. So this is the standard RNN, the single layer. The hidden state can be computed by the previous state and the current input. Sorry, here is t, not t-1. So now we try to change this operation to the Tensor-Power recurrent models. So idea is we use the multilinear product. We first concatenate the current input and the previous hidden state as a long vector. Then we do the multilinear product with weight tensors. And we can do this multilinear product for p times. So it's equivalent to do the tensor fusion as we show in multimodal learning. For the p-order tensor fusion, then we after this, we have a fully connected layer, G. By using this, actually, we remove the nonlinear activations. Instead, we use this tensor fusion to generate the nonlinearity. And based on this framework, we show that if the P is large, we can give us long memory, and a small P will let us short memory. But when the P is large, the algorithm is unstable due to sometimes the gradient explosion occurs. To further solve these issues, we wonder if we can learn the P from the data. But the P is the order of tensor, it's integer. So instead, to do this, we give a more strict assumption. We assume the tensor weight tensor G is symmetric. Then furthermore, we assume the G can be decomposed by the symmetric tensor decomposition. Then this layer operation can be converted as such formula. So compare this to standard RNN. We can see that we change this layer as an ensemble of R layers. So it's an ensemble of several different subnets. And each layer is with weight parameters with the input and the past hidden state from previous time with the power P. So that means our nonlinear function is the P polynomial function. And we have several subnets. And furthermore, we want to learn the P. So we change the P from discrete value to continuous value, and we use some kind of a gradient descent method to learn the optimal T. And for the time series data, if each time point, the data have also the high order tensor structure. And if we have the missing point on a specific time point, we don't have a continuous time series data. So this is a very popular applications in video with missing frame or the stock market price prediction. So we hope to build a model which can train the model from such time series data with missing time point. And we also hope our model can be predictive for continuous time point, not only for the discrete time point. So if we use tensorized neural network or RNN, it's incapable to handle such kind of irregular time points, and it's not able to prediction for continuous time points. So if we use neural ODE, and this method doesn't consider the tensor structure for each time point. To solve this, we combine this idea together. We propose a tensor neural ODE. So we have a time series data, which is a tensorial time series data. Now we try to build a model to learn the derivative of such time series data. So that means if we give an initial point y, we can just compute the integral of this model with the distance between the initial point. We can compute prediction for any time point. And to capture the data structure, we changed the neural network model to the tensor contraction layer. So we found the 3 different metrics for the projection or transformation on each mode, and plus the nonlinear activations. So in the end, I will introduce some new trends and directions in this field by other researchers. For example, some researchers from physics field, they built the machine learning model using such tensor networks for unsupervised learning, supervised learning, or generative models. And they apply the nonlinear mapping for the input layer and apply the tree structure tensor network. It's similar to like dimension reduction, like kernel PCA or something like that. And then on the top, they apply tensor network for classifier. Or some papers use Mila or more complicated tensor network models. They can achieve the performance is comparable to the state art, but still a little slightly worse. Also, the hybrid model to combine the deep learning like CNN as the first step to extract the latent representation. And after that, they apply the 2-dimensional tensor network as a classifier. And such model can give better performance than using the standard CNN with a fully connected layer. Also, quantum machine learning is attracting more and more attention in recent years. And Google released the TensorFlow quantum library in 2020. So here we show that this is a standard quantum neural network models. The difference is input is quantum state. And if we want to use quantum machine learning to process the classical data, the first step, we need to encode the classical data into the quantum circuit as a parameters or as a operations to encode our classical data here. After that, they apply many quantum circuit to do the transformation, and similarly, several layers to give the output. The output is because it's the quantum state, so they need the measurement to get concrete values. And also borrow the idea from machine learning, they can build the loss function to adjust the parameters in the quantum circuit to find the model parameters. And some researchers show that tensor network can be conveniently converted to the quantum circuit, like hierarchical Tucker can be converted as the quantum circuit conveniently. But there is some limitation or constraints that each tensor cores must be unitary operation. And the tensor chain can be also converted as a quantum circuit. So by using this, the tensor network, purely tensor network models can be run on the quantum computer. And it shows that robustness to noises and also such tensor network circuit provide the qubit efficient schemes. So finally, in summary, tensor network are useful tools for representation of high order structured data, and also useful for efficient reparameterization of deep neural network models. And some theory shows that tensor network have expressive power similar to deep neural network. But I think the performance still, there is some gap between the deep neural network and tensor network. So the reason, I guess, is tensor network are only have multilinear operations. It lacks of nonlinearity. And in the future, we are more interested in to investigate the robustness of tensor network models to the adversary attack and the interpretability of the tensor network-based models. Because tensor network is multilinear operations, so we assume the interpretability should be better than the neural network. So finally, I would like to thank my team members, especially some postdoc and visiting scientists and other part-timer interns and the remote collaborators. Thank you very much.
Thank you, Jibin. So questions for Jibin. There's one on the Q&A chat, Jibin, if you would like to take a look.
Okay. Yeah, the question is, hello, thank you for an interesting talk. I have a question about compressing weight of neural network by tensor train network. Does this compression increase or decrease execution time in practice? Yeah, it's a good question. So basically the computation is same or even the better, because the parameters are much less than the original weight parameters. And due to the tensor network operations, if the input layer is tensorized as a tensor, we can apply the tensor network operation that connect the core tensors individually. So the computation will also improve, but not dramatically. It depends on the rank.
Actually, Jibin, there are also some sketching approaches that could give you some quick computational benefits. I think Joel Trapp had a paper for compression, approximating tensors via sketches. So you could have, for example, your tensor network and its sketch. So maybe you can do something quickly with the sketch and then complement things with the actual tensor network. There could be many ideas that are interesting. I like this particular approach.
Yeah, exactly. Yeah, I know this. Actually, we also have one paper to do the sketching for the tensor ring decomposition. So we can, there are many problems how to sample the data efficiently and how to do the sketching using the less number of data to develop the method to reconstruct original data precisely. Yes.
There is one more question, but not on Q&A. So on chat, I think somebody wrote, how do you calculate distance in tensor network?
I'm not sure what you mean the distance, but if you apply the, for example, if you want to compute the traditional distance, you can vectorize the tensor network as a vector, then you can compute the distance by inner product or some L2 norm, L1 norm, or different distance or matrix. But I think your question is you want to ask how to compute the distance efficiently by using tensor network structure, just to use core tensors. I think, as I know that the inner product between the two tensor network can be computed efficiently. But if you do the just the summation minus, if one tensor network minus another tensor network, I think there's no good way to compute by the core tensors, as far as I know. But some operation can be computed efficiently. We don't need to make contraction of tensor network to original space. We just compute on the core tensor space very efficiently. Yeah, I hope this answered the questions for the ICA.
Can I also ask a question?
Yeah.
I think this is a kind of typical question you will have. But so given the tensor, tools, so how can you find the suitable structure given data?
Yeah, that's right. Because currently researchers using the manually choose that this structure or that structure. Basically, they just choose a very popular structure like tensor chain or tensor ring or hierarchical Tucker. But how to find the optimal structure, which probably will be random. And as I shown in the slides, we have tried one step to solve this problem, to find the structure. But still, it's only for the data. Given the data and tensor data, we try to find the completion task. But if we apply this idea to the deep neural network weight compression, it's still, we don't know how to find a good structure for compression the weight in deep neural network. But if we have a, yeah.
So, you know, for the architectures in neural networks, people do what is called as neural architecture search. And there are some popular formulations with optimization darts and so on and so forth. You could envision maybe another optimization formulation for tensors, and there things could also work as far as I'm concerned. What do you think about this?
Yeah, right. We also think about this, and we discuss how to maybe a neural network architecture search method can be applied to tensor network
I think it can.
search. Yeah.
Masashi's question is really on the point, yeah.
Right.
And I have one more question. So do you still have something to say?
No.
So my second question is about non-linearity. So as you said, so tensors have nice multilinear structure, but suppose we want to incorporate some non-linearity in the system. So how can you do that in a computationally efficient way?
Currently, I didn't see any paper to consider nonlinearity in the tensor networks. The only nonlinearity is generated by the input layer. So they change the input to nonlinear mapping to the rank 1 tensor. But I think I have some idea, but not we didn't know how it works, if possible. We consider after each layer, the tensor network transformation, we can impose simply the nonlinearity to the each core tensors.
So what happens if you have like pre-processing, non-linear pre-processing, and then tensor factorization, and after that you have another non-linear transformation, then have another tensor transformation and things like that.
Yeah.
You repeat this in an alternate way. Can you still compute everything in a computationally efficient way? Yeah,
if we impose nonlinearity on the whole output of the layer, we cannot use the efficient computation. But I mentioned I want to see that if we impose nonlinearity to the each core tensors, so then we didn't change the tensor network structure after the layer. So yeah, because if you apply nonlinearity to the whole output, so you need to contraction tensor network to original space, then the computation efficiency will be loose. So I'm thinking to impose nonlinearity to the each core tensors.
I see.
Instead of the whole output.
So in the case of like matrix, what does it mean? So you compute eigenvectors and apply nonlinear transformation to eigenvectors or something like that? If for the matrix case, if we have a matrix W and you decompose W as A multiplied B. So, and the input layer X transformed by the A and B. After transform A, we give the nonlinearity, and after B, another nonlinearity. So if we use the nonlinearity after input 2 through the A and B together, it's same as original neural network, just the compression the weight. But if we impose nonlinearity on each factors, it may generate different. It's not equivalent to the neural network with only compression the weight. And hope that it performs better than the original one. Yeah, hope so. But I'm afraid it's not easy to achieve the better performance. I see. Thank you.
Thank you, Chibin.
Yes, thank you.
I guess this concludes the talk. Thanks all for joining the talk, and thank Chibin for a great talk.